Okay, welcome to Forensics Investigations, and this is a session on network forensics. What I'd like to do is to recap some parts of networking. So for those of you who have done network fundamentals last year, and all of you are currently doing intermediate networking this year. So we're going to recap some of that. We're going to recap what network forensics is, why it is, how we can go about doing it. Some little bit on advanced techniques, a little bit on Tor. I might mention some about the FBI attack, and then a little bit on malicious traffic and how you're able to identify that. So we'll start off with a networking recap. So if we're sending traffic over a network, all of our data is going to be encapsulated in a packet of some kind, and we tend to think of these packets as being envelopes that contain messages or more envelopes, because our raw data from the application layer is then going to be encapsulated in something on the transport layer, like transmission control protocol, TCP, or the user datagram protocol, UDP, which is then going to be encapsulated in IP, the internet protocol, which is then going to be encapsulated in a layer 2 protocol. Let's call it, I don't know, IEEE 802.3 Ethernet. And so your data is going to be encapsulated in lots of different protocols, all have functionality for different parts of the network. Now, each of these packets or overriding envelope is routed, and the example is usually given that it's much like the postal system. So hopefully this recap is fine. It's going to be very easy for you guys to remember it. Here's an example. And this is an example of, over on the left hand side here, we have one PC, we have another PC over here. We have an application that's being used, and the application example is FTP, and we then have that FTP information being put into the transport layer. So we're using transmission control protocol here, TCP, which is then put into IP, which is then put into Ethernet. And that Ethernet connection goes from the network interface card of this host to the router over here, whatever that happens to be. And then the router is going to strip off the layer 2 header and add its own layer 2 header as it propagates it through the network. So we're always going to have, at every router, we're going to have this physical layer information being rewritten. Oh, Jesus. It's a network access token ring, which is entirely possible that it moves at a router. So we're having we have our Ethernet envelope here, our header here, which is then overwritten with token ring header. Highly unlikely to see it nowadays, but yes, that's entirely possible. And then above that, so at this section and above, well, we have exactly the same. So from IP and above, nothing changes on the router. The router is only going to overwrite the layer 2 header. And then eventually it's going to be received by the host, who's then going to strip off the physical address, which happens to be a token ring network, strip off the IP address. It's been received on the correct interface, and yes, this is the correct IP address associated with the host. Strip off the TCP, so it identifies what port this application, this packet is directed to, so what application this packet is directed to, and then the application is then able to use the information that is contained within the packet. So people think that networking is incredibly complicated. It isn't. It really isn't. It's not complicated, it's just complex. There are a lot of things that happen on a host machine and on the intermediary devices. And this is sort of another picture of what we've just been talking about. We'll have our data at the application layer. That data is then put into in this case we're using UDP, so user datagram protocol at the transport layer. And then that information, so the UDP header and the data, is then put into an IP packet. So we're adding an IP header here, and then that is then put into some layer 2 frame. It's odd. One here we call this a packet. We call the whole of this here a frame. Sorry, once we get down to layer 2. And of course, at each stage, we're adding our transport layer header, our internet layer header, and then our link layer, our layer 2 header. Now, very commonly, At the transport layer, we will use TCP, or we'll use UDP. Let me just correct this slightly here. Sorry, I didn't notice that earlier. TCP is a transmission control protocol. It's typically referred to as being reliable data transfer. And that is followed up by a bullet point here, which is entirely correct, saying it is actually just sort of faked over unreliable UDP. So is the remote host expecting data? Well, we're going to establish some connection, and as a part of that connection, we're going to establish some numbers that will identify these packets that we're transmitting. So if you receive packets out of order, you're able to renumber them, put them in the right order. If you don't receive a packet for a number that you're expecting, we assume that that packet has been lost and we ask for a retransmission. We don't ask for a retransmission, sorry, we retransmit. And then, have we finished having the conversation, we're able to perform some closure of the connection. UDP, so user datagram protocol, doesn't allow any of that transmission control. It does add only a source port and destination port in the header, so it doesn't have anywhere near the amount of functionality as TCP. And using UDP or TCP, we can have a whole range of port numbers. We've got 65,536 of them. And a port is just essentially something that will be tied to an application. So your application may well have a port that is open and is ready to receive connections. And in this example here, we have a remote server that has port 80 open. And port 80 is typically associated with HTTP. It also has port 25 open. Port 25 is typically associated with SMTP. So your PC, you're using your browser, you want to get access to whatever web page is being served by this remote server. Your browser will open up a port, to start with it will send a TCP, it'll actually send a TCP SYN packet as a part of the three-way handshake. And then once that connection has been established, it will no doubt send a HTTP GET request that is then serviced by the remote server. Now, please bear in mind that your PC, your browser, Chrome, whatever, is not sending from port 80. It is only sending to port 80. You would typically find the number given here is an appropriate number for your web browser to use to send traffic. Now, why is that? Well, let's say Chrome, you have 3 browser windows open and you're playing 3 different YouTube videos. Each of those different YouTube videos should be associated with a different source port so that you're not receiving YouTube data that's getting mixed up in Chrome. Anyway, I hope that makes sense. We then have some application layer protocols. We've spoken a little bit about these in reference to internet browsers and reference to email forensics. And here we have a classic HTTP, so we have a version HTTP 1.1, we have a GET request, and as a part of this GET request, we're able to see what the destination host is, www.telegraph.co.uk. We're able to see some information about what the user is using. So the user appears to be using Mozilla, or they might be using Safari or Chrome, what the user can accept, what encoding, what language, what char set, some cookie values. So we have lots of information that is included in the application layer that may well be sent along with as a part of the traffic. If we have a look at raw IP headers, we can see, well, here is something that's ripped off directly, almost the request for comment, the original RFC for IP. And we have a variety of different fields within the header, so version, IHL, type of service, total length, identification number, flags, fragment offset, time to live, the protocol used, header checksum, source IP address, destination IP address, options of which there can be many and many and many, and then some padding to ensure that your options will be, in the end, some multiple of 32. And I believe that we can see in an IP packet. So this is taken directly from Wireshark. We have our lower level, our layer 2 information here. If we expanded this, menu here, we'll be able to see some information about the internet protocol, which is exactly what we're seeing here. We're seeing version number, we're seeing the IHL value, we're seeing type of service, and then that gives us the ability to extract directly from our IP the information. In fact, you can pretty much, hopefully I don't have to click all that again, but you can pretty much see all of this. Bear in mind this is UDP I'm using here, but here we have Wireshark live. I'm able to go into the internet protocol. I'm able to see what version layer, what version we're using, what header length is. Referred to here as being differentiated services field. So this is actually the quality of service. What does it refer to here? Type of service. Length of that, the identification number, any flags, the protocol that's being used, and I don't appear to have any options. I do have a time to live of 113, so I can go. This packet can be transmitted across 113 hops before someone will decide to kill it. Let's hopefully get back to that page. Right. Okay. So what is network forensics? Well, network forensics is looking at network traffic for forensic purposes. And the problem with this is that network traffic is volatile. You can generate lots of it, and it only exists for a short period of time. And so you can, if you really want to, capture everything. If you do capture everything, bear in mind that, I don't know, you have a let's make this calculation easy, an 80 megabit per second connection at home, which of course is going to generate 10 megabytes of data every second. And that's going to require a large hard drive if you start multiplying that by a certain number of seconds, minutes, hours, days, weeks, years. It may be that you want, instead of capturing everything, you want to sample, and there's a protocol that enables you to do this, a protocol called IPFIX, that enables you to sample communication that's taking place between peers. It may be that you're able to identify particular things in a packet stream that you believe are interesting, and so you only decide to capture those. Now, why is it that you'd want to do network forensics? Well, you're able to catch people in the act, you're able to see things that are happening in real time, or you're able to discover information that perhaps isn't stored, so you can discover phone calls. So voice over IP, you're able to capture all the voice over IP information, it's not encrypted, you can replay the phone call. It may be that you're able to replay a network-based attack, and a network-based attack tends to be thought of as being a denial of service attack, in order to identify what happened. In order to do network forensics, you do need to typically have an understanding of some application layer protocol. There are lots of them. If you look on Wikipedia for the number of application layer protocols, there are loads. Predominantly because so many were developed for particular individual applications. Now, so much stuff goes over HTTP that specialist applications tend not to be used quite so much. You are able to extract lots of information through Wireshark. We've used that a lot. You can build your own custom protocol parser. You can do a whole load of things with TCP dump if you want, in order to perform forensic analysis of network traffic that is being captured. Now, it is in the UK, Section 2 of the Regulation of Investigatory Powers Act 2000 makes it an offence to intentionally intercept communication and private communication without lawful authority to do so. And you can get interception warrants if you really want. And of course, if we think that it's in the national interest of the UK for this information to be intercepted, there we are, safeguard the economic well-being of the UK, then that can also be done. Now, where is it that you'd wish to capture traffic? So if you look at, and I state Akami, because Akami produced some very interesting reports. So Akami produced a State of the Internet report, so it's quite an interesting read to see what type of traffic they have being sent over their network. They also have a security supplement to the State of the Internet report, which is quite an interesting read as well to see what type of network-based attacks have been occurring over the last quarter, what type the Akami network has seen. The Akami network are a content provider. So they host and they have a lot of network traffic traversing their network. And there is an example, and this looks like it's drawn in Packet Tracer, Cisco Packet Tracer. So this is a nice home network here. We have something referred to as being an internet here, and we have a nice little server network over here. So whereabouts do we want to capture traffic? Well, I want to capture traffic at this PC, this PC, this PC. I want to capture traffic at this router, this router, this router, and I want to capture this PC and this PC. In fact, why don't I just capture all the traffic going through the switch as well? And of course, the problem with that is the amount of data that you're collecting. It's just far too much. So inbuilt into your routers, you do have the ability to collect IPFIX information. In your inbuilt, no, I don't have one of those. You have the ability to collect IPFIX, okay, which is sort of a sampling of the network traffic that is being sent. So the question is where to capture. Well, somewhere on the route of traffic which you're interested in, typically internet server route. And this is a huge simplification. Okay, it's only a simplification because we've only provided more of a network at the home network and the server network. We haven't provided more of the internet. Of course, you can't draw the entire internet, or if you could, it does look very complicated. But it may be that, okay, from a server point of view, we would like to see what is going on within our own network. So we may be sampling, or we may be capturing traffic constantly at the switch, perform some data analysis on it, and then sending those reports to some reporting service somewhere. And we can, if we're on the local area network, we can capture traffic which is going across the local area network by asking the switch to mirror all of the ports, or we can. They said we can perform some hacking ways around that, and the hacking ways are to do with. I mean, you might be doing something called ARP spoofing, so that's the address resolution protocol spoofing. You may be doing some other things that are related to how nodes store ARP information, so you may be able to overflow the ARP tables. But there are some hacking ways that you can bypass the switch, only ensuring that traffic goes from one interface to another. If you want to capture internet traffic, you ideally want to capture at the router, so all traffic leaving the network, coming into the network, or if you're an ISP, you can capture at any other point that you own. If you are able to capture on the user's PC, then that of course gives you the fantastic ability to see what traffic is coming to and from that user's PC. Now, I've already given some examples with Wireshark, but here we have an example of some traffic capture on Wireshark, and the packet that happens to be highlighted happens to be packet number 25. Or what can we see taking place here? We have two internal IP addresses, so 10.10.10.70 and 10.10.10.10, and 10.10.10.70 appears to be making a request, and so therefore we're going to assume that 10.10.10.10 is a server, because that request is a HTTP GET request. Now, as a part of that HTTP GET request, I assume that there is already a TCP connection that's been established. After the GET request, it appears that the server services that GET request, and we have acknowledgement for the information is being transmitted, and then we have HTTP OK. We then make another GET request. We're sent some data, and we sent an OK message, and we send an acknowledgement for that. And so we go through. That's quite interesting. We then have a connection here, so the server is then attempting to make a connection. Sorry, the client is then attempting to make a connection to the server, and it appears that that connection is established, and that is a connection on the server at port 4444, and it is from the client at port 1036, and that's using TCP protocol. So we can see an awful lot here. We can see that there's some random index.php GIF. We can see that there's some information being stored on the server. We can actually rebuild that information based on the traffic that is being sent here. I've already mentioned the fact that if you are going to capture lots and lots of traffic, you do need a large amount of storage space. And also, if you are going to capture all of the traffic, you are going to have an awful lot of noise. So you're going to have a lot of other people's traffic, a lot of stuff that isn't actually relevant. I do need to make a very quick change here because unfortunately Gareth has not used a capital M to indicate that it is megabits per second. So let's make sure that is the correct unit. Now, if we're using Wireshark, please internet work. Wow, the marvels of modern technology. If we're using Wireshark, we may want to perform some form of filtering on the traffic that we've captured. There we are. And that filtering we can do for those of you who did the digital forensics unit in the first year. That will this is a bit of a recap for some of the stuff that we're doing in Wireshark in the first year. For those of you who haven't done this before, you're able to filter out a lot of stuff in Wireshark. I daren't flick between. Oh, let's do it anyway. So I can go into Wireshark here. I can type in. I'd only like to have all of the stuff that is running HTTP, and then I have all the stuff which is HTTP being sent here. So actually, I only want all of the stuff which is an IP source address of 192.168.1.100, and I need to put some double equal signs in there, and then I get all of the stuff which is IP address 192.168.1.100. So in Wireshark, we can perform. My computer's now indicating to me that I'm offline, which is rather sad. In Wireshark, we can perform some filtering in order to filter out packets of information. Now, it is also possible to perform some tracing. So we can trace to some IP addresses. And we can also use a set of databases that allow us to turn an IP address into some domain that owns that IP address. And so Gareth has provided a link here for GeoIP that enables you to see whereabouts in the world an IP address is registered to. In fact, it only gives you the address of someone to contact who is associated with that IP address range. And you also have the ability to use trace route, which rather coarsely uses some ICMP messages in order to trace a route. I'm just going to pause recording for a second. Right, hopefully I've started recording again. Yep, good. So we can go back to IP tracing. And the fact that, well, I was just talking about the fact that we are able to perform a trace route. We're also able to look at an IP address and associate that IP address with some geographical location. We've sort of covered a variety of different web applications. It may be that you're able to have some form of interaction through the web application using JavaScript. There are some other protocols or some concepts you should be aware of, like AJAX, asynchronous JavaScript, and XML, or REST, representational state transfer, or RESTful web services. And these sort of things will, in your web browser, act as an application and make requests to the server sort of on your behalf. Typically in order to get access to new information, to ensure that the web page that is being served to you as a browser remains current. And I have some examples of HTTP. So here's an example of some HTML. And this HTML, as we can see here, has this action. So the action is a post action, it's a HTTP post action. And that post is going to send some information in text. So that text is going to be available for you to see if you capture this traffic. And it's going to have some variable names and some data associated with those names depending on what you input into these boxes here. So you're able to intercept this. You're actually able to see the information that's being posted if you do a packet sniff, a packet capture. As we can see here, which is exactly what Gareth has done. So within our packet, we have names equal to Gareth, email equals Gareth Owen, ampersand at port.ac.uk, and telephone number is his office phone. A Facebook chat, or I've already referenced this before, you can pretty much see what this is. So here we have a load of JSON information, and this JSON information contains some indication of some times. So this time looks very much like it may be epoch time, and we may be able to see that as a part of the network traffic. If, however, the connection between the server and the client is encrypted, and typically that is HTTPS, so that's HTTP wrapped in secure sockets layer SSL, it's very difficult for us to decrypt that information. There are some tools that we can use. We can perform a man-in-the-middle attack if we could possibly perform a man-in-the-middle attack, depending on whether certificate authorities are being used. We can force users into sending unencrypted traffic, but typically those are, if you encrypt traffic, as in if you encrypt anything, it is difficult to decrypt. So we have to use other techniques in order to get access to that information. I have a few slides on voice over IP. So as I'm doing right now, I'm recording my voice. Now, if this is sent over a network, there are a variety of different protocols that will send. Sorry, there are a variety of different encoding algorithms that will send information across the network, and what will happen is we'll have to break whatever is sampled down into very small time samples, so that the audio is sampled. The example given here is 10 milliseconds. Each sample is then put into a packet, not necessarily a UDP packet, but put into a packet and sent to the remote computer. The remote computer receives a sample and asks the question, have we already played packets after this time? If so, discard. If not, play when that packet is due. And so voice over IP is a fantastic thing. You have lots of small samples being sent, lots of small packets being sent, to ensure that sort of normal conversation takes place. If we're able to capture all the traffic, we're able to replay that session. There are a whole variety of different approaches to achieving this, though. Google Chat, Facebook Chat, Skype, SIP RTP combination. There is something called a session initiation protocol, which establishes a call, a voice over IP call. There's a protocol called RTP, and there's a control protocol associated with RTP called RTCP. But you may find that voice over IP is just running, bland over TCP. The important thing is that the application layer, you're able to extract those samples and then replay those samples, put those samples back together and replay them later. Now I have a few slides about Tor. I referred to this briefly in the previous presentation on file sharing. And Tor is the onion routing network. The purpose of it really is to hide your IP address. In doing so, it also encrypts and hides the information that you're sending. So that is really quite a nice thing to have. Any intermediary computer system doesn't know that you're who you're communicating with and that you're communicating with them. So here's how it works. Your data is going to be encapsulated or encrypted in a lot of information. It's using multiple. It's going to be encrypted using multiple encryption keys, let's say. And so I have. Well, I'm going from my data, my unencrypted data. It's going to be wrapped up in different layers of encryption. This is what we see here. And so I need to encrypt the bit that was going to be decrypted by C, my exit node. I need to encrypt the bit that is going to be decrypted by B, my relay node. And I need to encrypt the bit that is going to be decrypted by C. So this bit, which is blue, my blue skin, just says, please send this to A. And A is then able to decrypt to read the bit in red. It can't read the bit in green because that's encrypted using B's encryption key. It certainly can't read the data. It's only C that is unable to read the data as it sends it out onto the network. And so A is unable to decrypt, send it on to B. B is unable to decrypt, send it on to C, and C is able to decrypt and send it out into the network. And this means that the data coming from here looks as if it's coming from C, which is really not so nice for C if that data or those requests happen to be towards a nefarious or a naughty server. In addition to the fact that Tor is able to hide your IP address and hide your requests, is the fact that there's something called hidden services within the Tor network, whereby you're able to establish a website that is in essence hidden and only accessible via a particular means, and that means is shown here, where Bob and Alice use their Tor circuits like normal. Yeah, that's absolutely fine. But we happen to have a hidden service inside the Tor network. And that hidden service you can access using, I've sort of given the indication here of a rendezvous point. So that rendezvous point is able to give information on a web server that exists within the Tor network, not outside of the Tor network. So an example of one of those hidden services is Silk Road. It was hidden. It was a large drug eBay type place. Apparently the founder had accumulated quite a lot of profit in bitcoins, and they were also able, once they'd identified the fact this was taking place on Tor, able to shut down any successors. There are techniques to identify where Tor hidden services are. So it is possible to be able to say which IP address is associated with a hidden service. And there are also options for something called a side channel attack, which I do suggest you take some time to read outside of this. So I'll move on to some other things associated with network and network forensics. Now, we are able to probe networks. You saw earlier we had this TCP connection. If I can go back to the Wireshark capture that we had, and on a Wireshark capture we had this SYN packet being sent, this SYN acknowledgement packet being sent, this acknowledgement packet being sent. This is the three-way TCP handshake, and this original SYN packet means that this port is a request to say, can I connect to this port number? And the SYN ACK being responded with means that yes, that port is open and looking to receive information. So let me just go back to where I was. So it is possible to ping. It is possible to do what I was just talking about, it's a TCP SYN ping, to identify people who hosts who may have particular ports open. In order to do this, we can script something up using a tool called Nmap. Nmap is a command line based tool that is able to do a whole variety of basic and advanced scanning for networks and hosts. I could do a demonstration here. Actually, for everybody on this course, in the next year you're going to be doing my unit called System Security. We go into Nmap in a lot more detail, so I'll leave that for the time being. What is referred to here is Nmap is going to do a scan on 256 computers on network 192.168.1.0 to .255. It's going to generate a lot of noise. It's going to be quite easily identifiable to an intrusion detection system that somebody's performing a scan of your network, and it is something that happens very often as a whole variety of people around the world learn that Nmap exists. There are some interesting hosts that are now connected to the internet. You would have heard of the Internet of Things. So pretty much every electronic thing may now have an IP address and is able to send and receive data. There are standard things you'd think about: servers, workstations, laptops, mobile phones, routers, printers, etc., etc. In addition to this, I'm not really too sure what this device is, but of course it appears to have been hacked in some way and has a very nice message saying, "Feed me a cat." In order to prevent your system from being hacked, or in order to prevent your system from responding to requests to see if ports are open, you may have a firewall running on it. And what is referred to here is a packet filtering firewall, which I believe you should have had experience with in the engineering networking unit, for those of you who are doing that as an option. So each packet that is received by our firewall software is checked against a list of rules. If the rule matches, and do what it says. And all these rules are tried and turned until there is a match, or until you get to the bottom which says allow the packet to go through. An example being if the packet is for TCP port 80, allow. If there's any other packet, then drop. And Gareth just had this interesting thing here called pivoting. So an attacker may well be attempting to get through the firewall to individual workstations. It may be trying to get through the firewall to get access to the Office server, but it can only get through the firewall, can only connect to the web server. But once it's connected to the web server and it's got access to the web server, it may be able to get access to other workstations or other servers, other systems that exist in the network. So there's a little bit of an overview of some old school attacking. Find a service that has a vulnerability, use a port scan to identify what services are running, and try a series of ports as the port is open, identify what that port is running, and there's a whole variety of ways we can do that. Here's one way, that I remember talking Gareth through many moons ago, which is using Telnet as an application. We're attempting to connect to the URL www.port80.uk at port 80, and when we do so, in fact, we see that the server is giving us a nice message saying, yep, the port is open, that's great, and we happen to be running this particular version of Apache with these modules, PHP, Perl, etc. So we have a lot of information about what the remote system is running that we may be able to find exploits for. And of course, from a forensic point of view, you want to be able to identify whether or not those exploits were, those vulnerabilities were exploited. So, the vast majority of traffic is unencrypted, although this is changing. Particularly Google doesn't have easy access to an unencrypted search engine. Finding interesting things is quite difficult when you have a large amount of data. Now, you have experience of following TCP streams, you have experience of using filters to filter out IP source, IP destination. If you have any encryption, if you're using something like Tor, it is very difficult to trace users. And networks aren't the only way that someone might find access to to services or information that is stored. Non-Wi-Fi wireless is becoming very common in electrical meters, burglar alarms, etc., etc. And these things may still be controlled remotely. Thank you for listening.